either in the form of gas or small bodies which collide with and adhere to the accreting body. Now, in the universe, there are numerous accreting objects which include protoplanets, protostars, black holes, and X-ray binaries. And since matter in the universe invariably possesses angular momentum, so accretion often occurs in the form of an disk. By studying the accretion process, we can extract important information about the characteristics of the central accreting object. As for example, if we consider an accreting black hole, then through studying the accretion process, we can get information about the mass and spin of the black hole. Accretion is a very efficient method of extracting gravitational energy, and also it is the principal mechanism of generation of high energy radiation in our universe. So in this picture, let us look at the accretion around a stellar mass black hole. So for example, let us say that we have a black hole and a companion star which are in a binary system. Okay. So due to extreme gravity of the black hole, matter from the companion star may get attracted into the black hole. However, since the companion star may have angular momentum, so matter cannot fall into radially into the black hole, rather it will form an accretion disk-like structure. Now we know that magnetic fields are invariably present in stars. For example, at an average location on our sun, the strength of magnetic field is around 1 Gauss. So due to magnetic flux freezing theorem, what will happen is that the magnetic fields will be drawn into the accretion disk, okay, through the accreting matter from the companion star, okay. And if matter in the accretion disk has to fall into the black hole, it has to lose angular momentum, okay, and so the angular momentum transport can happen due to the viscosity. Also, the viscous dissipation can cause the heating of the accretion disk, okay, and the disk can also cool down due to various radiative processes, and we can observe these radiations from the stellar mass accreting black hole in the form of X-rays, which can be in the form of soft X-rays as well as hard X-rays. Now these X-ray radiations are regularly observed from space-based satellites like Astrosat, NuStar, RxD, Maximum Newton, etc. So now let me discuss about the significance of magnetic fields in the accreting phenomenon, in the accretion process. Okay, so for the first time, Lyndon Bell in the year 1969 and Shakura and Sunya 1973, they showed the contribution of magnetic fields to the angular momentum transport in the accretion disks. Today morning, Indu has very well explained the Blandford and Nake process as well as the Blandford and Payne process. Okay, so let me just have a recap. So Blandford and Payne in 1977, they proposed that relativistic jets may be launched from the vicinity of the black hole through the rotational energy of the black hole, okay, via the torque exerted by the magnetic field lines which are threading the black hole horizon. In an alternative mechanism, Blandford and Payne in 1982, they suggested that the spinning black hole can actually cause the ordered magnetic fields in the accretion disk to correlate with the accreting matter, and this mechanism can also drive quasi-relativistic jets through the release of the gravitational potential energy. Again, Balbus and Hawley in their seminal 1991 paper showed that magnetorotational instability may give rise to this viscosity, where even a weak magnetic field, okay, can cause the accretion flow to become turbulent, okay, thereby leading to the outward transport of angular momentum. We continue with our introduction, and I would like to point out that many observations have confirmed that most of the black holes in the universe are rotating, and some of them are in fact rapidly rotating. Okay, so in order to study the accretion phenomenon and around a rotating black hole, we need a proper general relativistic treatment. Okay, or alternatively, we need to use an effective potential okay, which must be included in the Newtonian approach. Another very important point is that the idea of subcaplarian transonic accretion flow around a black hole, this idea was initially put forward by Muchortsev and Paksinski in the year 1982. And later on, this idea of subcaplarian transonic accretion flow around black holes was later on improved by many other authors such as Chakrabarty 1989-1996 and Mukhopadhyay 2003. Again, numerical simulation studies suggest that the toroidal component of the magnetic field in the accretion flow, it dominates over the other components. For example, the poloidal component. Okay, so in our work we considered that the accretion flow is threaded by toroidal magnetic fields. Okay, so magnetic field is given by B phi cap, and in such a case a proper magnetic induction equation must be considered while modeling the accretion flow. So here in this particular figure I have shown the schematic picture of magnetic field line inside the accretion disk. So the figure on the left shows an axisymmetric disk which is threaded by a mean azimuthal magnetic field. So here the B phi component is non-zero, however the radial Bx component is 0. And in the figure on the left shows the turbulent disk with mean azimuthal magnetic fields and fluctuating magnetic fields. Okay, so due to the non-linear growth of magnetorotational instability, this mean azimuthal magnetic field line can develop fluctuating components. So it is to be noted that if we take the azimuthal average of the fluctuating radial components, they will average out to 0. However, the product of the Bx and B phi component, it always has a negative value. So the azimuthal average of the Bx B phi cannot be neglected, and this will contribute to the Maxwell stress in the accretion flow. So here I have shown the basic picture of magnetic flux advection with mass accretion rate in the accretion flow. So this picture, figure 2, shows the vertical cross section of the accretion disk which is threaded with toroidal magnetic fields B phi. Okay, so m dot here represents the mass accretion rate, and phi dot represents the magnetic flux advection rate. So the black hole is situated at the origin of the coordinate system, and we assume the cylindrical polar coordinate system. Zeta is a parameter which parameterizes the advection rate of the toroidal magnetic field. Okay, so if zeta is greater than 0, then the magnetic flux advection rate will increase as the matter approaches the black hole horizon. Now let us discuss the model assumptions. So since we are dealing with rotating black holes, so to take into account the effect of space-time geometry around a rotating black hole, we make use of the pseudo-Kerr potential introduced by Chakrabarty and Mandal 2006. The use of a pseudo-Kerr potential helps us to avoid the general relativistic treatment while providing results which are close to the general relativistic treatment within some limits. So the Chakrabarty and Mandal 2006 pseudo-Kerr potential can effectively mimic the space-time geometry around a rotating black hole for spin parameter ak less than equal to 0.8. And we use the geometric unit system where the gravitational constant, mass of the black hole, speed of light are all considered to be unity. To study the magnetic activity in the disk, we make use of the plasma beta parameter, which is defined as the ratio of the gas pressure to the magnetic pressure in the accretion flow. And the decay of magnetic fields through the magnetic reconnection mechanism can cause a large amount of magnetic energy to get dissipated in the accretion flow, and thereby the accretion flow can get heated up. Okay, and due to high temperature in the accretion flow, the matter will remain in the ionized form. So in the magnetized accretion flow, the electrons can effectively lose energy via the synchrotron radiative process. So the synchrotron radiative process we consider to be the active cooling mechanism in the accretion flow. Okay. So in this particular slide, I have shown the form of the effective pseudocar potential that we have used in our work. Okay. So for more details on this pseudocar potential, I refer you to the paper by Chakravarti and Mandal 2006. Now let me discuss the governing equations. So in order to model the dissipative accretion flow around the rotating black hole, we must consider a set of magnetohydrodynamic equations, and we will do the study in the steady state. Okay, so the MHD equations we consider in the steady state. The first equation we have to consider is the mass flux conservation equation. Secondly, we have to consider the radial momentum equation. Thirdly, we have to consider the azimuthal momentum equation. Thereafter, we also have to consider the entropy equation. Okay, and the hydromagnetic flow equations must also be supplemented by the induction equation as given by equation number 5. Now, in the accretion flow, the Maxwell stress transports the angular momentum. Okay. Now, when the velocity in the radial direction is significant, okay, in the accretion flow, then we assume that the x5 component of the Maxwell stress, Tx5, is proportional to the total pressure of the accreting matter. Okay, following the work by Chakravarti 1996 and Machida et al. 2006. So the Maxwell stress Tx5 is considered to be proportional to the W plus sigma U square. So W here represents the vertically integrated total pressure in the flow, and sigma U square represents the ram pressure in the flow. So the ram pressure contribution we have to take into account when the velocity in the radial direction is significant in the accretion flow. Okay, so alpha beta here is the constant of proportionality. Okay, now we come to another important assumption. Okay, so which gives the prescription of the advection rate of toroidal magnetic flux phi dot. Okay, so now the simulation work by Machida et al. 2006 has shown that in the quasi-steady state, the magnetic flux advection rate in the accretion flow varies as 1 over x. Okay, so basically due to the magnetic diffusion term or due to the dynamo term, the magnetic flux advection rate doesn't remain constant radially. Okay, and on the basis of this simulation result and following the paper by Oda et al. 2007, we introduce a parameter zeta. Okay, and thereby the dependence of the magnetic flux advection rate on the radial coordinate x we parameterize as phi dot goes as phi dot injection multiplied by x injection whole to the power minus zeta. Okay, so phi dot injection here is the magnetic flux advection rate at the injection radius or at the outer edge. Okay, now if this zeta parameter is equal to 0, then the magnetic flux will remain conserved. So phi dot will be same as phi dot injection throughout the radial direction. Okay, however, if zeta parameter is greater than 0, then the magnetic flux will increase as the accretion flow will approach the black hole horizon. Now we discuss about the solution procedure. Okay, so using the equations given by equation 1 to 6, so equation number 1, 2, 3, 4, 5 and 6, these 6 equations we will solve simultaneously in order to determine the gradient of radial flow velocity. So du dx is the radial gradient of radial velocity, which takes a form of some numerator by denominator, where the numerator is a function of the radial coordinate, the radial velocity, the sound speed, angular momentum beta, and the denominator is also a function of the flow velocity, sound speed, and the plasma beta parameter. Okay. Now the radial velocity gradient of the flow along the streamline must be real and finite everywhere. That means when the accreting matter is going from the outer edge of the accretion disk and entering into the black hole horizon. So throughout the radial velocity gradient of the flow must be real and finite everywhere. Okay, throughout the length scale of the accretion disk. However, if at some radial distance xc, okay, if the denominator goes to 0, if the denominator in this expression goes to 0, then we must have that the numerator must also simultaneously vanish at that location xc, okay, in order to maintain the smoothness of the flow. So these conditions are known as the critical point conditions. Okay, and so by supplying the boundary conditions, so suppose the boundary conditions can be at the critical radius xc, we supply the angular momentum lambda c and beta c, and thereby we can obtain the radial velocity and sound speed uc and ac at the critical point. Okay, so by using the equations d is equal to 0 and n is equal to 0, we can get the radial velocity and the sound speed uc and ac respectively at the critical point. Now, if the values of the radial velocity gradient du dc at the critical point, if they are real and of opposite sign, then the critical point or the sonic point is called as x type. Okay, whereas if they are real and of the same sign, then the sonic point will be called nodal type or n type. Whereas if the du dx at the critical point, if these values are imaginary, then we get a O type critical point or O type sonic point. Okay. Now in accretion flow, the saddle type sonic points are highly important because the accreting matter passes through saddle type sonic points only. Alright. So, okay, now I come to another important feature in accretion flow, which is the phenomenon of formation of shocks in accretion flow. So today morning Indu has also shown some results from numerical magnetohydrodynamic studies, where he showed the formation of shock waves in the numerical simulation. So in astrophysical systems, we frequently encounter flows which contain the propagation of shock waves. Okay. Now, while we study the accretion flow around a black hole, the existence of shock waves in the global accretion solutions, they are highly important. Okay, because they can explain a large number of observational aspects from the black hole candidates, like the quasi-periodic oscillations, the accretion disk luminosity. Okay, all these features can be very well explained through the shock phenomenon of formation of shock waves. Now, when do the shock waves occur? So, such shock accretion solutions we can get when the supersonic accretion flow, which approaches a black hole, experiences a centrifugal barrier in the vicinity of the black hole. The accreting matter possesses angular momentum, and due to this angular momentum, the accreting matter experiences a centrifugal barrier in the vicinity of the black hole. Okay, and when the supersonic accreting matter experiences the centrifugal barrier, then shock waves may emerge. Now, due to this centrifugal repulsion, the supersonic flow may undergo a shock transition, and when supersonic flow undergoes a shock transition, the supersonic flow becomes subsonic. Okay, and the post-shock corona becomes hot, dense, and puffed up. Basically, what happens? A shock is a very thin region where the flow variables, accretion flow variables like the density, temperature, the flow velocity, the sound speed, they undergo a sudden and drastic jump. All right. Now, whenever dynamically feasible, the discontinuous shock jump in the accretion flow, they are preferred by the second law of thermodynamics, okay, because the global transonic accretion solutions, they have an opportunity to increase their entropy. The entropy of the flow increases after the shock transition. So whenever dynamically feasible, the discontinuous shock transitions in accretion flow are favored by the laws of thermodynamics. Now the formation of shock waves in plasma are governed by certain conservation equations which I have shown here. So here plus denotes the quantities evaluated immediately after the shock. So plus denotes the post-shock quantities and minus denotes the quantities evaluated just before the shock. That means minus denotes the pre-shock quantities. So in order to have the formation of a stable shock wave, we must have the mass conservation, the conservation of mass across the shock front, okay. The mass accretion rate must remain continuous across the shock front. Then we must have pressure balance condition across the shock front. Then the specific energy of the flow must remain conserved across the shock front, as well as the magnetic flux advection rate should remain conserved also across the shock front. So in case these four conditions are simultaneously satisfied, then we can get the formation of a stable shock solution. About the influence of the spin parameter on the position of the shock transition. Okay, so as I already told you that accretion flow around a black hole is essentially transonic. So accreting matter at the outer edge will be subsonic, and this accreting matter must fall into the black hole horizon supersonically. So evidently the accreting matter must pass through a sonic point and it must become supersonic before entering into the black hole. So in this particular plot here, I have shown in the top panels, I have shown the variation of the Mach number with the radial coordinate. Okay, so Mach number is basically defined as the ratio of the flow velocity to the sound speed in the accretion flow. So here we have injected matter from the outer edge, which we consider to be 1000 Schwarzschild radius, with some given fixed parameters like the beta parameter at the outer edge, the angular momentum at the outer edge, and the specific energy at the outer edge. Then the viscosity parameter and the accretion rate we have kept fixed, okay. And the angular momentum at the outer edge we have considered to be a subcaplarian angular momentum, and this and matter with this given boundary condition at the outer edge, when it approaches the black hole horizon, then the subsonic matter becomes supersonic after passing through a sonic point x out. Now this sonic point x out is situated very far away from the black hole horizon, and it is called as the outer sonic point or outer critical point. After passing through x out, the accreting matter becomes supersonic, and in the vicinity of the black hole, this supersonic matter can undergo a centrifugal repulsion. Okay, it can experience a virtual centrifugal barrier, and thereby the density will keep on piling up. Now when the density gradient approaches a critical limit, then this supersonic matter can undergo a shock transition, and thereby it can become subsonic. So the Mach number decreases. We can see the vertically downward arrow shows the shock transition. So after the shock transition, matter becomes subsonic, and the subsonic matter can again fall into the black hole after passing through another sonic point x in. Now this sonic point or critical point x in is located closer to the black hole, and it is known as inner sonic point. So after passing through inner sonic point, matter becomes supersonic again, and the supersonic matter can enter into the black hole. Now in this figure A, the spin parameter of the black hole is chosen as 0.32. So this is a very quite a slowly rotating black hole. Okay. So corresponding to this Mach number, okay, this particular solution in the plot shown in the bottom in the left, we have shown the corresponding this one variation of the plasma beta parameter with the radial coordinate. Okay, so plasma beta parameter, we can see that it gradually decreases as the flow approaches the black hole horizon, thereby indicating that the matter is becoming magnetically dominated as it approaches the black hole horizon, and across the shock transition the plasma beta parameter undergoes a downward jump. Now we come to figure B here. So here what we have done, we have kept all the flow parameters fixed at the outer edge, and we have increased the black hole spin parameter to 0.52. So this is AK 0.52 will refer to a moderately rotating black hole. So in this case, when flow is injected with the same boundary conditions, then what happens, we find that the position of the shock is shifted away from the black hole horizon. Okay, so since the black hole spin parameter has changed, so what is happening, due to the spin orbit coupling in Kerr geometry, the angular momentum profile of the accretion flow is gets modified, and so the centrifugal barrier gets weakened, and thereby the shock is positioned away from the black hole horizon. And here also in the bottom panel, the variation of the plasma beta parameter is shown with the radial coordinate. Here also the flow is getting magnetically dominated as the matter is approaching the black hole horizon. Now we come to the another result, where we have tried to study the effect of the accretion rate and the zeta parameter. So zeta parameter, we recall that it is the parameter which prescribes the magnetic flux advection rate. Okay, so how the accretion rate and zeta parameter affect the shock location, let us see. So here also at the outer edge of 1000 Schwarzschild radius, we have injected matter with some subcaplarian angular momentum with some specific energy beta h, and the spin parameter here we have chosen to be 0.8. So this is a case of a rapidly rotating black hole. Viscosity parameter we have fixed, and we have injected matter with zeta 0.6 and accretion rate 0.05, and thereby the black vertical arrow shows the position of the shock jump for zeta 0.6 and m rate 0.05. Now keeping the accretion rate fixed to 0.05, we have increased the zeta parameter to 1.0, and thereby we find that the shock location shifts towards the black hole horizon. So with the increase of zeta parameter, the magnetic flux advection rate is increased, so synchrotron cooling becomes efficient in the accretion flow, and since the density is the post-shock density is much higher, so synchrotron cooling will be much more effective in the post-shock flow, and thereby the post-shock pressure will decrease, and the shock location can get pushed towards the black hole horizon. Okay, again in the third case, what we have done, we have fixed the zeta parameter to 1.0, and now we have increased the accretion rate to 0.45. So when the accretion rate is increased, then also the amount of magnetic fields carried with the accreting matter will increase, synchrotron cooling will become efficient, and since cooling will be much more efficient in the post-shock region due to the high density there, so the post-shock pressure will further reduce, and shock front will further be pushed towards the black hole. So the conclusion from this figure is that apart from the accretion rate, the zeta parameter also significantly affects the shock dynamics in the accretion flow. Now corresponding to the three shock solutions shown here, we have studied the various flow properties. Okay, various flow properties, and considering a 10 solar mass black hole. So here in figure A shows the variation of the flow radial velocity as a function of radial coordinate, then the density of the flow, then the magnetic field strength, okay, then the electron temperature profile, then the disk aspect ratio, and the effective optical depth in the accretion flow for the three cases shown here. Okay, we have presented here. So we can see that the flow, the density of the accreting flow, or the electron temperature, the magnetic field strength, or the effective optical depth, all of these, they increase as the matter approaches the black hole horizon, and also across the shock transition there is a drastic increase in the density, electron temperature, then magnetic field strength, and effective optical depth. Here we can see that the disk aspect ratio also has a significant jump across the shock transition. Okay, and throughout the accretion flow, the disk aspect ratio remains well below unity throughout the accretion flow. And if we consider the radial velocity, then the flow velocity increases as the matter approaches the black hole horizon, and after the shock jump, the flow becomes subsonic, so the radial velocity decreases, and again the radial velocity increases as the matter approaches the black hole horizon. Okay, so now in this particular plot we have studied the variation of the different shock properties as a function of the zeta parameter. So the different flow properties we have studied are the position of the shock location, the shock compression ratio, and the shock strength. So shock compression ratio is defined as the ratio of the post shock vertically average density to the vertically average pre-shock density, and the shock strength is defined as the ratio of the pre-shock Mach number to the post-shock Mach number. Okay, so here the flow is injected from 1000 Schwarzschild radius with some fixed values of beta h, specific energy, the Kerr parameter chosen is 0.8, and viscosity, and the different Leinsteins here correspond to different values of angular momentum at the outer edge. Okay, so we have chosen three different values of angular momentum. For each of the cases, we find that as the zeta parameter is increased, the shock location is shifting towards the black hole horizon, and after a given value of zeta parameter, the shock location is not possible. Okay, and corresponding to the shock solutions presented here, the corresponding shock compression ratio and shock strength are also found to increase as the zeta parameter is increased. Okay, again, the blue curve corresponds to the highest angular momentum at the outer edge, and the black curve corresponds to the lowest angular momentum at the outer edge. So if we consider a given value of zeta parameter, suppose zeta 0.8, then when the matter is injected from the outer edge with lower angular momentum, then the shock location shifts towards the black hole horizon. This happens because we know that shocks are centrifugally driven. So if the centrifugal repulsion becomes weaker due to the decrease of lambda h, then the shock location will shift towards the black hole horizon, and thereby the compression ratio and shock strength will increase. So in the next plot, we have studied the variation of the shock location as a function of the accretion rate for three different values of the zeta parameter. So we can find that for all, here also the matter is injected from the outer edge with some fixed values of beta h, specific energy, and angular momentum, Kerr parameter, and viscosity parameter is also fixed. So for each value of zeta chosen, we find that the shock location shifts towards the black hole horizon as the accretion rate is increased. So with the increase of accretion rate, we have already seen that shock location approaches towards the black hole horizon. Okay, now for a given value of accretion rate, if the zeta parameter is increased, so this blue curve will correspond to the lowest value of zeta, and the black corresponds to the highest value of zeta. So for a given accretion rate, when the zeta value is increased, we again find that the shock location shifts towards the black hole horizon, which we have also seen previously. So now in this particular plot, we will study the parameter space which is scanned by the critical accretion rate, okay, versus the viscosity parameter. And we have studied the parameter space for closed accretion topologies as well as standing accretion solutions. Okay, so numerical simulation studies have shown that if the entropy at the inner sonic point is greater than the entropy at the outer sonic point, if this holds, but if the shock location, if the shock conditions are not perfectly satisfied, then what will happen? We can get oscillating shocks. Okay, so uh, yeah, so here in this particular plot, we have shown we have shown the C represents close accretion topologies. Okay, and so the region of C, they consist of standing as well as oscillating shocks, and the S here corresponds to the standing shock solutions. So we can see, and we have chosen here three different curve parameters. So as the curve parameter is increasing, so this parameter space of standing shock is decreasing. I think I don't have much time, so let me quickly show the other results. So here also, by fixing a given part curve parameter, I have shown the parameter space of critical accretion rate and viscosity for different values of beta in at the inner sonic point. So if beta in decreases, that means the flow is more magnetically dominated, and in that case the parameter space for standing shock is reduced. Okay, so beta in 100 corresponds to a larger parameter space as compared to beta in 5. So in the next plot, I have shown the variation of the critical accretion rate as a function of the beta in at the inner sonic point, and I have chosen two different curve parameters, AK0 and 0.8. So we can see that for both the cases, for both the curve parameters, a wide range of beta in supports the accretion solutions, and if beta in is smaller, so beta in less than 1 will correspond to a magnetically dominated flow. So magnetically dominated flow sustain shocks for lower value of critical accretion rate, whereas for high value of accretion rate flow, the critical accretion can be larger. Whereas if we go to higher curve parameter, again the parameter space is reduced. Okay. So this is the last plot, I mean last result. So here what we have done, we have considered dissipative shocks, where we have considered that the fraction of energy is dissipated across the shock front, and for these 9 we have taken the values of the black hole mass radiation parameter from the literature, and we have tried to model the maximum dissipated energy across the shock front, and thereby we have calculated the shock luminosity using this relationship, and we have compared the maximum shock luminosity calculated from our model with the radio jet kinetic power that we get from the literature, and for most of the cases we find close agreement between the shock luminosity predicted from our model with those observed in the literature. For this particular case, LMCXT, we couldn't find the reported value in the literature. So with our model, we can predict the maximum shock luminosity that we may expect. So okay, this is another plot which shows the variation of the dissipated energy as a function of accretion rate. Let me not discuss this in much detail. So basically, let me come to the conclusions that we have obtained steady global accretion solutions around a rapidly rotating black hole, which contains shock between the inner and outer sonic points. And we have found that the rapidly rotating black hole, for fixed injection parameters at the outer edge, it holds stationary shocks for a wide range of the zeta parameter, angular momentum, plasma beta, black hole spill parameter, and accretion rate. And the post-shock corona or PSC is likely to be the region of likely to be the launching region of relativistic jets. And for 9 stellar mass black hole candidates, we have found close agreement between the estimated radio jet kinetic power from our model with those reported in the literature. So that is all. Thank you very much, and I look forward to questions.
Yeah, so thank you very much, Dr. Shukar, for your nice presentation. Yeah, so now the session is open for discussion. So I request participants, if you have any questions, you can ask Dr. Shukar is here.
So,
So Dr. Shukar, question is there from the audience. So thank you very much
no
for
issues. Thank you very much.
yeah. So next, I'll request Mame Achi.
No.
Mame Achi
Hello, sir.
start his presentation. His
Sir,
topic is
am I audible, sir?
accelerating universe.
Okay.
Yeah, yeah, you are audible.
Okay.
So your topic is accelerating universe in FR gravity. So you'll be given 15 minutes for presentation, and in between that discussion is also there. So basically you'll get 12 or 13 minutes for your presentation and 3 minutes for a discussion or any question will be there. So over to Tamiyachi. So keep
Sir, my
continuing.
slide is visible, sir.
Yeah, here is visible. Please continue.
Okay. Okay. Good afternoon, everyone. Uh, my name is Tameachi. I'm a research scholar in Department of Physics, Rajiv Gandhi University. I'm pursuing a PhD under Dr. Sanjit Singh. And the title of the paper that I'm going to talk today is Accelerating Universe in FFR Gravity. This will be the content that I will follow. So, in the last few decades, we have observed that the universe is not only expanding, but is changing over time. The universe is
Kami
expanding,
di
is changing.
panagre pa
So,
paida. Ya,
hello.
kaya ron hey, ako na. Wali sa sige no isi ngren hey.
Excuse me.
Yeah, Mr. Talem, please. Yeah, so
Okay.
he has muted.
Okay.
He has muted, so you
Okay.
can continue.
Okay. So we have evidence for the accelerating expanse of the universe. So, but the problem with the accelerating expansion of the universe is we don't have any theory that perfectly explain why the universe is accelerating. So we have one model like dark energy, which has partially able to succeed to explain the accelerating expansion of the universe, but we are yet do not understand what dark energy. Even the classical Einstein field equation hasn't been successful, and there are other branches of physics which have tried, but has not been able to explain this phenomenon of the universe. But in order to deal that, uh, there is an alternative way to solve this problem. We call it modified gravity or FFR gravity. So many authors has proposed their model. So in our paper, we are proposing this FFR gravity, which is a function of scalar curvature R, and the model I'm proposing is R FFR equal R plus alpha R square plus beta R cube minus e to the power 4 by R minus lambda to the power 8 by R cube. So using this FFR model, we'll modify Einstein field equation and we'll try to understand the dynamic of the universe. The modification is done by considering the Einstein-Hilbert action, uh, and we included uh, our FFR instead of the scalar curvature. So we take the variation of action of equation number 1 to get a modified Einstein field equation. So Einstein field equation, the modified one is given by equation number 2. So we have two terms here in the right-hand side of equation number 2. That is the first one, the T mu nu. That one is effective energy tensor due to the curvature of the universe, and other one T m mu nu. That one is due to stress energy tensor due to matter field. For our purpose, we have nullified the matter field, so we are only considering only the space of only the geometry of the universe, and we study how the geometry of the universe changes over time. So the modified Einstein field equation that we have got, the solution for that modified Einstein field equation, we use a robot worker matrix to find a solution for that. And
Tame, you got muted. Kindly unmute yourself. Kindly unmute yourself, Tame.
Tami, if you hear us, kindly unmute.
Okay, sir. Am I audible now, sir?
Yeah, you are now audible.
Okay,
Yeah.
okay. Thank you.
Please continue.
Okay. Again, from equation number 4, we define scalar curvature in terms of scale factor given by equation number 7. Now, to find the dynamic of the universe, we have considered two cosmological parameters here. That is Hubble parameter in terms of scale factor, and deceleration parameter Q in terms of scale factor and Hubble parameter, represented by equation number 8 and 9. And considering the solution we got in equation number 5 and 6 and 8, we solve equation number 10. Then since we have considering our model to be f of r given by equation number 11, where alpha, beta, mu, and lambda are coupling parameters or coupling constant, we put those value in equation number 10 and solve for Q and Z, Q and H, using numerical techniques. So that solution is given by this highly non-linear differential equation, equation number 12. So equation number 12, it has equation number 12, we have coefficient B, C, and D. So B, C, and D itself contain both function and the variables H and Q. So that's why it makes it very highly non-linear differential equation. So this is coefficient B and C and D. Okay. Solve equation number 12. Again, we use numerical techniques, and we have found this plot. Before we discuss about the graph, about this graph we got, I'd like to highlight. Okay, so to solve the equation number 12, so we have considered two initial boundary condition for Q and Q prime. So the value for Q and Q prime was taken by hand, such that it fits with a desired plot we wanted. Okay, and the value for Q we have taken minus 0.5, and for Q prime we have taken 1.655, and also we have considered H equal to 1 to be the present universe. So this graph is a Q versus H plane. So Q, since it is a deaccelerating parameter, so positive Q represent the deacceleration of the universe, and negative Q represent the acceleration part of the universe. So the nature of the curve, this is obtained by putting also the coupling parameter like alpha, mu, beta, and lambda to be 2, 12, 8.65, and 4 respectively. So this is what we have got. We can see from the graph that the universe has undergone transition from deacceleration to acceleration in the past universe, since H equal to 1 is our present universe. And since H is a function of time, inverse function of time, so all the values where H is less than 1 represent the future of the universe, and all the value where H is greater than 1 represent the past of the universe. So in the past, we can see the universe has undergone transition from deacceleration to acceleration, and the transition point is represented by number 1, where the where the value of H is 1.322, and from there it is in accelerating universe, and it reaches up to 2, which is the present universe, and it is accelerating, we can see from the graph. And our model also shows that in the future, this acceleration of the universe, the current acceleration of the universe, will not gone forever, but rather it will end up to a peak value, that is 3, and again it will go. It will move towards a new approach or new phases of towards the deacceleration. Okay, depending upon this initial values and coupling parameters, this new transition in the future may occur, which we will see later on. Okay, so when we vary the value of initial value Q in the range where Q less than -1, so we find that the universe tends to go a never-ending acceleration, but we cannot conclude that this never-ending acceleration lead to a big grief of the cosmos, because our equation is highly non-linear. So we cannot conclude whether this graph shows if the universe will go a big grief. So again, from here we can see that Q, the value of initial value of Q, as we have taken from -5 to -1, it varies, and there is a dependency of initial value of Q in our model. Also, for the another initial value, that is Q prime, we have varied the value for initial value of Q prime from 1 to 1.655, and rest of all the parameters and initial values are kept similar to the figure for 1. So again, we can see that there is a variation in the nature of the curve, and we can see that the transition point from deacceleration to acceleration shifted toward left with respect when we increase the value of Q prime. And also in the peak value, we can see that the present accelerating universe diminished with initial value is reduced, and it will reach to a new epoch in earlier with a smaller value of Q prime. And this graph shows the sensitivity of the Q prime. Regarding the coupling parameter, the first variation we have done with alpha, So we vary the value of alpha in the range from 2 to 120, and we see that the nature of the curve, it varies. And we can see that the transition point from deceleration to acceleration depends upon the changing value of alpha, and also the peak value, it does change, depends on the value of the alpha. And similarly, taking the same idea, we have mu. We have changed the value of mu from 1.8 to 1.86 to 8.40, and we find that the transition point from deceleration to acceleration, it remained independent in the value of alpha, but in the post-universe, the nature of the universe, it depends upon the mu. And this is lambda, and from here we can see that the nature of the curve, it depends upon the value of lambda in the post-universe, but it's not depend in the transition point that happened in the past. And this one is beta. Again, the initial value, the beta value remain independent when the universe transits from deceleration to acceleration, and in the post-universe we see there is a dependency of beta. Now, now again we have defined a new term, that is redshift parameter Z in terms of scale factor. So we have Hubble parameter H, which is in terms of scale factor. Then we have deceleration parameter Q in terms of scale factor. So we use all those equations and we construct this equation number 14. This is again a non-linear differential equation. It contains both H, Z, and Q, and the prime it's with respect to H, and we want to find a solution between Z and Q, the deceleration parameter and redshift. So from equation number 14, it is not possible to solve directly because we have H also included here. So what we have done is we already have one differential equation from equation number 12, which is a relation between Q and H. So we combine this equation number 12 and 14, and we took a parametric numerical solution for Q and Z. Since Z is a function of H and Q is a function of H, so we find a relation between Q and Z numerically and solve to get this graph. Here, this multiple curve is due to we have taken the initial value in the ranges. So, for example, there's two red line you can see. The two red line represents the value of initial value of Q from 0.1 to 0.3, and so for Q prime, it is represented by blue line, and it is the value is 1.2 to 1.8, and initial value for Z is 0.2 to 0.5, and for Z prime 1 to 4, which is represented by green line. So since this is Q versus Z, again we can see that the universe is undergoing transition, has undergone transition from deceleration to acceleration, which is very anatomical from the universe. Then and all those value of Z that is intersecting.
Mr. Tame, your time is almost over. So please,
okay, it's almost done, sir.
Quickly.
I'm almost done, sir. Okay, I'm on. So all those value that intersect Q equal to 0, the value of Z, they are called transition redshift. So it is observed while varying the initial value of Q and Z prime from 0.1 to 0.3, and 1 to 4, we see the transition red shift, the value of transition red shift decreases. On the other hand, the initial value for Q prime and Z when taken from 1 to 3 and 1.6 and 1.2 to 1.3 respectively, we find the transition red shift increases. And to plot this, since we have also considered the value for alpha to be 500, mu to the power 4 equal to 10, beta 41, and lambda equal to 7. And this one is the last one. So in these figures, what we have done is we have varied the coupling parameter individually, and we have found that as we change the value of this coupling parameter, our plot changes. We have alpha, because initially the alpha value was taken 500, changes into 804, and this graph is different from the figure 7. And similarly for mu, lambda, and beta we have done. So in conclusion, we have considered an FFR model to modify Einstein field equation, and we plotted Q versus H, Q versus Z graph for different values of coupling parameter, that is alpha, mu, lambda, and beta, to describe the evolutionary phases of the universe. For Q versus H, present accelerating scenario of the universe is obtained, and so that the universe has undergone transition from deceleration to acceleration phase in the recent past. For Q versus Z, also shows transition of the universe from deceleration to acceleration phase. So nature of the expanding universe in the past, present, and the future, and transition redshifts depends upon the value of the coupling parameters and the initial values of Q and Z. Thank you. Okay, I'll take, if you have any queries or suggestions.
Thank you, Tame, for your presentation. A quick 1 or 2 questions from the participants, then we can ask the next. Any questions?
Hi, I want to ask a question, or maybe not exactly question.
Yeah.
Can you hear me?
Yeah, you're audible. You're audible.
Actually, I don't know much about this, but I am wondering, like, this, when you modify the gravity, you introduce all these parameters like alpha, beta, mu, lambda,
yes,
lambda, and means how we can constrain, like, what should be its value, or how we know with observation or maybe theoretical prediction how to constrain this value, what should be this value, or maybe can you say something about that?
Okay, like we have here, alpha, beta, mu, we have to consider those value by ourselves only, and we have to consider those values in such a way that it fitted with what is being observed in the universe. So in our case, since you can see from our graph, also.
Okay, so thank you very much. So any other questions?
Okay.
Any other questions? Okay, then I can call the next speaker. Next speaker is Dr. Seshadri Mojumdar, who will be speaking on wideband view of high-frequency QPOs of GRS 1915 plus 105 in software variability classes observed with AstroSet. So I request.
Hello?
Yeah, you are audible. So please continue, Dr. Seshadri.
Okay, so my screen is visible?
Yes, yes, it is visible.
Okay, thank you. Good afternoon, everyone. So today I will be talking about wideband view of high-frequency QPOs of GRS 1915 plus 105 in software variability classes observed with AstroSet. So my collaborators are Santobroto Das from IIT Guwahati, Anuj Nandi from ISRO Bengaluru, Tilak Katok from TIFR Mumbai, Srihari from IIA Bengaluru, and Nafiza Aftab from Bengaluru as well. So first, the black hole X-ray binaries. So in a black hole X-ray binary system, so the center black hole accretes matter from its companion star and forms a disk-like structure, what we call as the accretion disk. Now, due to the presence of various viscous effect, the infalling matter becomes very hot, and essentially it emits in electromagnetic radiation. So for black hole binary systems, the radiation is mostly in the X-ray waveband, and for a black hole X-ray binary system, the radiations can have different origin. So the basic one is the thermal component, which generates due to the accretion of matter. So soft photon ejects from the accretion disk, and a part of this thermal component can actually get inverse comptonized into the hot electrons present in the corner structure and can produce the high energy power law tail. Now, it may also happen that a part of this high energy component also can reprocess again in the accretion disk, and that can create the reflected component as we can observe. Now, the most studied and most interesting phenomena of black hole X-ray binaries is the quasi-periodic oscillations. So this can be associated with the rapid variability that is present in a given time series. So from observation, what we have, the photon count, which is plotted in a given time series. Now, if we have any kind of signal or any kind of feature in this light curve or in this time series, so it is impossible to extract that information from this curve because of its randomness. Now, one have to go to the Fourier domain of this particular time series. Now, if we go to the Fourier domain or in the power density spectra, we can often see this kind of narrow peaks. So that we called as a quasi-periodic oscillation. Now, in the power density spectra, these quasi-periodic oscillations can be fitted with Lorentzian profiles, and it characterized by basic three factors. One is the quality factor, which essentially tells how much coherent the peak is. Second is the fractional RMS amplitude, which indicates how much power content is there with a particular detection. And the last one is the significance, which tells how much significant the detected peak is with respect to the error in the power density spectra. Now, depending on the frequency range of these QPOs, they can be classified into two separate classes. So the low frequency one having the frequency less than 30 Hertz, and in the high frequency regime, the frequency varies from 30 to 450 Hertz. Now, it is well known that these low frequency QPOs are actually connected to several spectral states of a black hole binary system. Now, what about the high frequency QPOs? Now, if we look at the frequency range of these high frequency QPOs, we can see that these frequencies are basically very close to the Keplerian frequency of matter, which is orbiting at the innermost stable circular orbit of a black hole. So it is obvious that this kind of feature generates from the region very close to the black hole, and essentially it will carry the effect of strong gravity of the black hole. So the study of high frequency QPO is very interesting and also very challenging. So recently we have looked into the astrosat observations of this source GRS 1915 plus 105 in softer variability classes. So we looked all the archival data from 2016 to 2021, and we find that the source was initially in the theta variability class, then followed by beta class, delta class, rho class, kappa class, omega class, gamma class, and finally chi class. Now, depending on the variability pattern in the light curve and also the distribution of points in the color diagram, that is basically the variation of soft color HR1 and hard color HR2, we can identify these classes as these soft classes. And also we see, so basically in this figure, these blue traces are the light curve, which is obtained from the LAX-BC data in 3 to 60 kV energy band. And in the inset, these red traces are basically the light curve corresponds to the SXT data. Now we see that in SXT data also same variability pattern is observed. Now, once we have identified these 8 variability classes, we generated the power density spectra in 0.01 to 500 Hertz. Now, once we generated the power density spectra, we see that these 4 classes, which is delta, kappa, omega, and gamma, actually shows high frequency QPO near 70 hertz. So in our entire analysis, the QPO frequency varies from 68 hertz to 72 hertz. And also we see that we have few observations in several classes in which we don't have the detection of high frequency QPOs. Rather, we have the feature of low frequency QPO with a second harmonic. So the frequencies varies from 3 to 7 hertz, and these features are actually the type C low frequency QPOs. But since we are interested in high frequency QPO only in this particular project, so we only discuss about the high frequency QPO features. Now, since we have the advantage of broadband energy coverage of 3 to 60 kV in lax PC instrument, so we intend to study the energy dependent behavior of these high frequency QPOs. So we have divided the whole energy band into three basic energy band, which is 3 to 6 kV, 6 to 25 kV, and 25 to 60 kV. And we find that this high frequency QPO feature is actually appearing only in this energy band, which is 6 to 25 kV. And this other two energy band, as you can see, is absolutely flat. And this trend is true for all these four classes in which we could detect the feature. And what is more is that the RMS amplitude as well as the significance of these detected QPOs are actually more in this particular energy band of 6 to 25 kV. Then we have omega class, kappa class, and gamma class observations in our analysis. So in these classes, we can see that in the light curve, a sufficient duration of high count is present, as well as low count dips are also present. So we were interested to find that which part of the light curve is actually generating this high frequency feature. So we segregated the whole exposure time into the segments of 32 seconds and obtained the power density spectra. And the result is as follows. We see that near 70 hertz, as indicated indicated by this color bar, we see that the power near 70 hertz is maximum whenever there is a long duration of high count rate. And when the light curve suffers a dip, the power is significantly less. So same trend is also true for kappa class observations. And in gamma class, we can see that the QPO is present almost persistently in the entire exposure time. So that is because we can see that almost the high count is present in the light curve, but near 500 to 750 seconds, the QPO is not that much strong because of this small duration of low count dips. So we conclude that these high frequency QPOs are actually due to the high count rate which is present in the light curve. So here also we have compared two separate power spectra, taking from the data corresponding to one dip and one non-dip. So in the top panel, we can see that this PDS corresponds to this part of the light curve, this red part of the light curve corresponding to the high count rate, and we see that the QPO is present and it is prominent. And in the low count dip, we can see that it is absolutely flat and the PDS is mainly noise dominated. Now, finally, to correlate these timing properties with the spectral properties of the source, so we have obtained the wideband energy spectra in 0.7 to 50 kV energy range from taking data from both SXT and lax PC, and we have fitted the whole energy spectra with NTHCOM and power law component. Now, in our analysis, we have few observations in which we can detect the high frequency QPO feature, and also we have a few observations in which the feature is not present. So we compared the spectral properties of these two classes, and we find that whenever the QPO is present in the power density spectra, the corresponding energy spectrum shows a dominance of the componentization component, or basically the flux with the NTH component, that is the contribution of this componentization is more with the presence of high frequency QPO. And also this gamma NTH, which is the photon index of this particular component, the NTHCOM component, is also found to be more in presence of high frequency QPO. Now in the color bar, we saw the percentage RMS amplitude of the high frequency QPO. so in which the QPO is present. And also we have calculated the upper limit of the RMS amplitude at the QPO frequency in those observations in which the QPO is not prominent. So we see that for those observations, the color is towards red, which also indicates the non-detection of QPO, and the maximum upper limit of RMS remains below 1. And for QPO detection, it is remain above 1.5. Now, in 6 to 25 kV energy band, we see that the QPO is only present in this particular energy band. So we intend to study the variation of fractional RMS amplitude in this particular energy band. So we find that the high frequency RMS amplitude increases with energy up to 17 kV, and then it again decreases. And in the color bar, we saw that the anti-Hitchcock flux or the quantization flux in this particular energy bands. And it is observed that this anti-Hitchcock flux is only prominent in between 6 to 25 kV. So beyond this energy range, the flux is absolutely negligible. So based on these results, we finally conclude that the high frequency QPOs produced in GRS 1915 plus 105 source can be due to the result of the oscillation of a quantizing corona, which is so the quantizing photons are actually creating the variability which produce the high frequency QPOs in this particular source. So these are the concluding remarks. So we have observed the high frequency QPO in these 4 classes, and the QPOs are found to be more significant with more RMS amplitude in this particular energy band. Also from RMS spectrum, we can see that the RMS amplitude is increasing with energy, and again it decreasing. And also from dynamic analysis of PDS, we see that the high contrast are actually responsible for the generation of high frequency QPO. And from the spectral and timing correlation, we can conclude that these QPOs are actually originated due to the oscillation of the quantizing corona near the source. So finally, I would like to thank the NEMA organization, the NEMA organizers for giving me the opportunity to present my work here. Thank you.
Okay, thank you very much, Dr. Seshadri. So, if any question, I can ask the participants. Quickly,
Yeah.
1 or 2 questions.
Hi, Sheshadri.
Hi.
Hi, nice talk. Could you please go to slide number 7?
Okay.
What do you think is the reason for not finding QPOs in the greater than 25 kV band? So is it due to the low flux of the data, LAX-BC data?
So in 25 to 60 kV, you are saying?
Yeah. Yes.
So actually, the thing is, this quantization component actually dominates up to 25 kV. So if you see the energy spectrum, so here you can see that the quantization component is actually dominating up to 25 kV. So after 25 kV, basically this power law line is dominating the energy spectrum. So, so basically these high frequency QPOs are actually due to the quantization, and which is represented by this anti-Hitchcock component. So, so we conclude that since it is dominating up to 25 kV only, so the QPO is only present up to that energy range.
Okay. And the low in the lower energy band, basically it's the black body component which dominates. That is why you couldn't get in 3 to 5. Is it so? Am I right?
Yes, it may be the reason, right?
Okay. And I hope the feature of this QPO should be present. I mean, even if we segregate the 6 to 25 into more narrow energy bands, and if we generate the PDS, I think the QPO feature we should find in, even if we make segments of the 6 to 25 kV energy band. Did you check that?
Yes, I checked that the QPO will be present, but the strength will not. The strength will not be that prominent.
Okay.
Because this entire energy band photons are actually contributing in the generation of this high frequency QPOs.
Okay. And one more question, one more query. I mean, you could find the feature of this QPO in data from each orbit that you considered.
Yes. So for a particular observation ID, I checked for all the orbits data, and so in most of the orbits data, the QPO is present. So for representation purpose, I took the maximum exposure orbit. The exposure, I mean the orbit having the maximum exposure.
Okay.
Yes.
Thank you very much.
Thank you.
Okay, thank you, Dr. Sarkar, for asking the question. Any other question? Okay, so if there is no question, then I should thank speaker for this nice presentation.
Thank you.
So now I would like to call Dr. Sapam Gayatri. The topic is so fermion tunneling across the event horizon of rotating BTZ black hole and corrections to entropy of the black hole on account of quantum gravity effects. So I request to start the meeting and start the presentation, and you will be given 15 minutes.
Yeah, sure, sir.
Yeah.
Good afternoon, everyone. I'm Sapam Gayatri. I'm a research scholar from Department of Physics, Manipur University. I'm working under Professor K. Jugindra Singh. The title of my presentation here today is Fermion Tunneling Across the Event Horizon of Rotating BTZ Black Hole and its Correction to Entropy on account of quantum gravity effects. I'll just give you a short introduction, then we'll move on to the formalism part. We know that black holes are they are perfect absorbers and they do not radiate any particle or any energy from or any radiation from it. However, when we take into a different perspective, its definition changes. So when quantum field theory with general relativity is taken into account, black hole emits radiation called Hawking radiation, named after Stephen Hawking. And many scientists and many renowned professors have worked under to find the Hawking radiation for different black hole systems. For example, I've just list down a few of them. I could list down all. So here, Parikin, Wilczek, Cross, Wilczek, Kerman, and they all studied the tunneling effect. Tunneling method for finding the Hawking temperature for different black hole system, and one of the method used here is a semi-classical tunneling method, which was proposed by Srivasan and Padmanabhan, where it gives a very simplified and conceptual understanding of the black hole radiation as tunneling of particle across the black hole event horizon. So we can redefine the definition of Hawking radiation as the quantum tunneling effect of particles at the horizons of black hole. So the essential idea here is that we are going to consider a particle and an antiparticle pair production at the near the event horizon of the black hole, and one of the particle will be trapped inside the black hole, and the other particle will try to move out from the black hole. So while trying to move out from the black hole, it will tunnel through the or it will tunnel across the event horizon of the black hole, and here the horizon of the black hole plays the role of the barrier. So if the particle that tunnels across the horizon, if it comes out and if it has positive energy, then can be stably exist in the universe, and that is what we see as radiation from the black hole. So let's go into the calculation part of how we will get the Hawking temperature, and how it is affected by when we consider the quantum gravity effect. So I use BTZ black hole in this particular talk, and BTZ black hole is a exact equation of Einstein field equation in 2+1 dimension, and it has a negative cosmological constant of -1 by L square, and this is the line element of the BTZ black hole, and it has two meaningful horizon, R plus and R minus, and where one is for the inner horizon and another one is for the outer horizon. Here we incorporate the idea of quantum gravity, and I'll just give you a short idea of quantum gravity because it's a very huge idea. I'll just give you a short. It is a consequence. We can say it is a consequence that leads from trying to unify the quantum mechanics and general relativity, and it tries to describe the gravity according to the principle of quantum mechanics. And when we try to, in doing so, the general idea of uncertainty principle gets modified into the equation that I've written here, where beta is equal to beta naught LP h cross square, where beta naught is the dimensionless parameter. And here, when we use quantum gravity, there are various theories like string theory and loop quantum gravity theory, and then this black hole physics or black hole physics theory, where it says that it predicts that there is a minimum observable length in the order of Planck distance, which is 10 to the power minus 33 centimeter. So from here, from this idea, the usual uncertainty principle or the standard uncertainty principle gets modified, and the corresponding commutation relation also gets modified. And by using the generalized uncertainty principle, we will use field equation here. For tunneling particle, we will use a field equation. So the particle that I consider here is a fermion particle. So for fermion particle, I use the Dirac equation, but the Dirac equation gets modified when we put into account the quantum gravity effect. So this is the generalized, I can say the generalized Dirac equation. So the aim for our paper is that we are going to solve this equation for the Dirac for the fermion particle that tunnel through the rotating BTZ black hole. So while trying to solve this equation, we consider the gamma matrices for the rotating BTZ to be this equation 1, 2, and 3, and we will incorporate this in this equation, in the Dirac equation, and we need a wave function to solve it. So the wave function for the spin-up particle is chosen by equation 4. I consider spin up. We can go for spin down particle also, but for spin down also, the wave function will be the same. And while solving the Dirac equation, we will get two decoupled equation, number 5 and 6. So by solving this equation 5 and 6, we can say by taking the determinant of equation 5 and 6, we get an equation of motion for the emitted fermion particles given by equation number 7. Now we are going to solve this equation to get the radial solution of equation 7. So this is the radial solution. Why am I solving the radial equation? Is because we are going to use WKB approximation method to get the tunneling probability of fermion particles, and we are going to compare that with the Boltzmann factor of the thermodynamics, because we need the temperature factor from there. So the radial part of the equation, from the radial part of the equation, only the imaginary part is going to be considered for finding the tunneling property or the tunneling probability. So the imaginary part of the radial equation is used. And here there is a Z factor here. This is a correction factor, I can say, because of the beta factor here. So this Z is nothing but this big term here. Okay, and from here we will compare with the Boltzmann factor of thermodynamics, and we get the temperature function here, or the final corrected temperature equation of rotating BTZ black hole. And here the TD is the original Hawking radiation for rotating BTZ black hole. And when we put beta to be 0, because beta is the correction factor for this particular equation 11. So when we put beta to be 0, we get the original Hawking temperature. So from this particular equation 11, we can give a conclusion here that on account of when quantum gravity effect is used, it lowers the rise of temperature of the black hole. This is the result that most of the papers that I have listed down before, most of the papers that they have discussed there also, they have mentioned there. So the same result I got in this calculation. So the rise of the temperature is lowered down when we consider the quantum gravity effect. And by using the temperature, we can get the entropy correction also. So in by using the first law of black hole thermodynamics, we calculate this entropy, and the entropy results out to be by equation 14. Here there are factors like delta 1 and delta 2 up till goes to delta 10. These are the correction factors, and in all these correction factors, I will show you the correction numbers here. On all these correction factors, there are beta terms everywhere. So when we put beta to be 0, the original the original Hawking temperature for rotating BTZ black hole is recovered here. So when we put beta to be 0, we get the original one. So the aim of my talk is that when we put beta to be 0, we get the original Hawking temperature, and we can conclude that when quantum gravity effect is put into account, the Hawking temperature gets corrected, and for fermion particles, it depends. Not only for fermion particles, we can consider other particles also, but for my talk is only for fermion particles. So on account of fermion particles, the Hawking temperature depends not only on the mass and the angular momentum of the black hole, but also it depends on the mass and angular momentum of the emitted fermion particle. As you can see in this equation, I'll go back and show you the equation for T. Here in the Z correction factor, there is a omega, there is m, and there's a small q, where these are the energy, the mass, and the angular momentum of the emitted fermion particles. And that's all for my presentation. Hello?
Thank you. So any questions? Participants, any questions? So you can ask. Okay, so if there is no question, then I should thank Dr. Gayatri for this nice presentation.
Thank you.
Now I would now like to call Ranchagiri Brahmo. His topic is gravitational deflection of light due to ellipsoidal celestial objects. So, Mr. Brahmo?
Yes, sir. Am I audible?
Yeah, you are audible. You can share your screen and start the presentation. So you'll be given 15 minutes for your presentation.
Is my slide is visible? Hello? 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 Yes, your slide is visible. You can continue. Okay. Good afternoon, everybody. Myself is Ranchagiri Brahmo. I'm working under Professor Ashok Kumar Singh in Department of Physics, Assam University, Silchar. Today I'm going to talk about the gravitational deflection of light due to ellipsoidal celestial objects. These are some outlines that can be described my today's talk. Introduction. We know that deflection of light due to massive objects was partially predicted by Albert Einstein in his general theory of relativity, and it was first tested in 1919 by Dyson and his workers. And then many people have studied about the deflection of light due to gravitation, and their study is mostly based on the spherical symmetric objects, where the gravitating object is considered as the spherical symmetric, and the angle of deflection obtained for that spherical object is given by delta phi is equal to 4h, where h is and by r naught, and this r naught is known as the closest approach. It is when the light is passing near a gravitating object. This r naught represents its closest distance
in its trajectory of light. But in actual celestial objects are not spherical symmetric in actual. These are of some ellipsoidal shape. This ellipsoidal shape of the gravitating object may be because of rotation or may some other factors may be there, and we uh, uh, in ellipsoidal when there is a three axes there alpha, beta, and gamma. When alpha is equal to beta and beta and gamma, this third axis, then this is known as the oblique, and others is alpha is equal to beta, which is less than gamma, and it is known as prolate. A spherical object is a special case of the oblique ellipsoid, we can say, when it is alpha, beta, and gamma all are equal, and it is known as the spherical. Uh, uh, Ellipsoidal distribution of mass distribution of mass may depend on rotational rotation of the gravitating object, also the matter or energy of the object from which it is made of. Now, how we measure the ellipticity of the ellipsoid, and this can be measured in a parameter known as the linear eccentricity, where we represented this parameter by A, which is square root of this alpha, alpha square minus gamma square, where alpha denotes the major axis of the ellipsoid, and this gamma represents the semi-minor axis of the ellipsoid. And for all positive values of A, this should be S squared, and it is known as oblique, you can say. And for negative values, it will be prolate, or if A is equal to 0, this will reduce to the spherical one. Now, what is the motivation of this work? We know that the symmetry of the space-time depends on the mass of the gravitating object, and hence, when it should be depend on the distribution of the mass. It should be related to distribution of the mass. So, the distribution of mass should be taken into account when we are studying about the uh, trajectories of the light, since this mass is the factor of the uh, symmetry of space-time. And in literature, we found that ER metric is Eros and Rosen metric, which is body object with quadruple parameter. That quadruple parameter describes the non-spherical distribution of mass. And we see that this metric obtained for the non-spherical distribution of mass by Eros and Rosen encounters very with complicated mathematical expression. It is very difficult to study with this metric, and only a few of works been found on that subject. For example, this I have given here. On the other hand, in 2011, we had found another metric element that can be described uh, symmetry of space-time due to ellipsoidal celestial objects found by NEMA-VII in 2011. And in current study, we took this line element obtained by NEMA-VII in 2011 as our mathematical tool for the geometry of space-time due to ellipsoidal gravitating object. And our objective is to obtain the deflection angle of light and to compare this value of deflection angle with rotational effect on light bending. Where it is the line element obtained by NEMA-VII this is given by ds square is equal to this one by represented by equation 1, where this question represents the square cell radius. A I have defined already. It's known as the linear eccentricity. Alpha and gamma represents semi-major axis and semi-minor axis respectively. Now, using this line element 1, we obtain a Lagrangian for the spacetime due to oblate ellipsoidal object. This can be represented by equation 2, where this t dot, r dot, theta dot, and phi dot represents the derivatives with respect to an affine parameter. Here we can see in this equation 2, that is the Lagrangian, t and phi are the cyclic coordinate. From that we can obtain two constants of motion, where it is represented by equation 3, is E and L. And using this equation 3 into this equation 2, we can obtain this equation for putting this f equal to 0. This f equal to 0 because for null geodesic, in null geodesic f equal to 0, and after substituting this equation 3 and rearranging, we obtain this equation 4. That is r dot square is equal to this one. And why we obtain this equation 4 is because we need to find the deflection angle. Now, what is the deflection angle? It is the angle that is the trajectory of light is deviated from the straight line. Is whether there is no object, light travels in straight line, but when there is a gravitating object, due to gravitation, it deviates from the straight line, then the amount of this deviation is defined as the angle of deflection of light, and it is represented by equation 5 mathematically. Then we consider that the light is traveling on the plane such that where theta is equal to 5 by 2, where theta is equal to 5 by 2. Then from equation 4, we obtain this equation 6 by substituting theta equal to theta is equal to 5 by 2. Then further simplifying this equation 6 reduced to this equation 7, where L is B is equal to L by E, then represents the impact parameter of the light. Slide is not
So, sorry to interrupt the Rajeshwari Brahma. So, please kindly
is not,
microphone once. It's not audible.
is it audible now? Hello?
Yes, now this time it's clear now. Please carry on.
Slide is not something problematic. Okay. And now we obtain this equation 7 by simplifying this equation 6, where V is represents the impact parameter. And from this, now we consider the case, special case, when the trajectory, when the light is approaching to the gravitating object and its closest approach denoted by R naught. Then since R naught is constant, then R dot equal to 0. And from that we obtain the relation between this impact parameter and R naught represented by this equation 8a. And after simplification, we obtain this uh, equation, QB equation 8 given by 8, and solution of this 8b can be shown as equation 9. And then, what is the angle of deflection? Angle of deflection here, this can be expressed or represented by the variation of delta phi coordinate with respect to r, and this can be obtained from equation 3 and 7. This equation 3 and 7 and can be expressed as equation 11. Therefore, light deflection angle from equation 5 by using this equation 11, we substitute this equation 11 into equation 5, then we obtain this general form of light deflection angle represented by equation 12. Now, this equation 12 is very, it's not an easy. Therefore, we substitute, we assume this psi square equal to this one r naught square plus a square by a square plus a square, r square plus a square. Then this gives this one r equal to this, dr is equal to this one. Then limit also changes as r tends to infinity, psi tends to 0, r tends to r naught, and psi tends to 1. And substituting all this into equation 12 and simplifying, we obtain a general form of deflection angle in simplified form, denoted by equation 14, where this p psi is equal to 1 by this one root over 1 plus a square by r naught square equal to 1 minus psi square, and this h is m by r naught. Further rearranging this equation 14, we obtain this one, equation 16, and where q psi is represented this one 1 minus psi cube p psi 1 minus psi square. Now for all a less than r naught, is we know that linear eccentricity and r naught is the closest approach. We yield this is less than or equal to greater than or equal to 0 and less than equal to 1. Then we expand this psi in this series given by equation 17. And using equation 17 into this q psi, this is equal to 1 by psi cube p psi and 1 minus psi square. Then we got this one, this series by denoted by equation 18. Then this equation 18 has a maximum value at psi equal to 1 is given by q 1 equal to half p plus square by
Mr. Brahma, Mr. Brahma,
yes sir.
finish
Yes
quickly.
sir.
Because, yeah.
Okay. Now we assume that trajectory of light is sufficiently far from the gravitating object when such that h is very less than 1. Then this term twice h qz equal to this h3 plus s square by r naught square is less than 1. Then this term 1 minus twice h q psi to the power minus 1 by 2 become analytic, and this can be expanded into a Taylor series given by equation 20. And substituting this equation 20 in the light deflection angle expression, then we found this series form of deflection angle 21. Then by integrating this 21 term by term, we obtain a series form of final deflection angle represented by equation 22. Here, A is the linear eccentricity, then substituting A equal to IA as the complex number. Then this equation 22 can be used for the prolate object. Then this equation also reduced to this standard form of deflection angle that is obtained by Newton and specters in series form. When A is equal to 0, this is reduced to series expression for spherical object given by equation 23. The results we obtain the deflection angle of light, that is the function of m, r naught, and a, where m is the half of the square radius, r naught is positive, s is the linear eccentricity. The deflection angle due to ellipsoidal object can be calculated by equation 22. We have already discussed. This equation is valid for a weak deflection limit. It is when the light is sufficiently at a far distance from the gravitating object for the trajectory of light when it is in the ellipsoidal plane, that is when theta is equal to pi by 2. We compared our then we calculate the deflection angle for Sun as our test object when
Dr.
by
Brahma,
assuming yes sir.
yeah, so finish quickly.
Okay. Then we have seen that contribution due to ellipsoidal object in the deflection angle is found much greater, sufficiently greater than the contribution due to rotating object. Then you can say that uh, ellipsoidal mass distribution cannot be neglected when we are studying the deflection angle of light or the trajectory of light. And these are the some curves when showing the angle of deflection due to Sun, and the Sun is for M59 galaxy. And this curve shows that the with increasing value of A, the deflection angle also increases. At conclusion, this one we obtain the ellipsoidal mass contribution of A is higher than the rotating parameter. Thank you.
Okay, thank you very much. So quickly, one or two questions you may ask participants. Okay, so if there is no question, then I should thanks speaker for this nice presentation. Next, I would like to call Dr.
Thank you, sir.
Yeah, thank you, Dr. Palay Kumar Kormakar. His topic is investigation of nucleus acoustic waves in degenerate quantum plasmas in compact astrophysical environments. Now the Dr. Kormakar, you may share the screen and may start the presentation. So you'll be given 45 minutes for your presentation. So don't worry.
Thank you. Okay. Thank you very much. Thank you very much.
Yeah, please continue, sir.
Is it visible?
Yes, sir. Yes, sir. It's visible, sir.
Okay. So first of all, I am extremely thankful to organizers for inviting me to share my work with you. At the same time, I congratulate both IUCAA as well as Rajiv Gandhi University for organizing such excellent program. Okay. So I am Pranay Kumar Kormakar, and accordingly, I have decided my title of my research work presentation as investigation of nucleus acoustic waves in degenerate quantum plasmas in compact astrophysical objects. And this work is carried out by myself and my research scholar, Shayanti Dasgupta. Okay, so this work has already been published in scientific reports. And here I'm just going to share some of the results based on this. And at the same time, this work connects to compact astrophysical objects. And let me use marker. Okay, so mostly we work in this area particularly. Oh, it is not working. Okay, fine. Particularly in this area, but this work connects to the compact astrophysical objects like your white dwarfs, and then your neutron stars, etc. So here, the density from the density temperature phase space, this is the region where this connects. Okay. So accordingly, my presentation will be of two parts. So part one, so that is your basic information, and part two, the applied results, what we have applied. So accordingly, the layout goes this way. Okay, first of all, the plasma is well known to everybody. So conventionally, we are familiar with 4 states of matter. And accordingly, it is only the temperature and the phase which decides the actual phase space, the thermodynamical parameters. So in case of your, if you see, in case of your solid, for example, your eyes, so you see the temperature is here. So this is your solid state. And at the same time, liquid state, we can see the temperature lies here in this regime. So this is liquid. And again, gaseous state. So this is at high temperature relative to this. But what would happen if the temperature is far away, far above this temperature? So in that case, what happens? Your hydrogen gets converted into protons and electrons. That is, ionization has taken place. And this state is well known as plasma state, a unique state of matter. So people talk about fourth state, but it is fourth is not a scientifically correct word, but unique state of matter, that is correct. Okay. Okay, and how to probe, as per our conception, probing inside atom. So from the atomistic point of view, this is our atomic model. So in atom model, what we get, these are your nucleus, and these are your orbiting electrons. And the orbiting electrons, we can see whenever it jumps from your higher to lower, what happens? Photon is energy is emitted. Conversely, whenever energy is supplied from external sources, the reverse effect is observed. Okay, so this is the main principle of plasma generation or plasma production. Okay, and this is simple, 1 electron and 1 proton system. So this is your hydrogenic plasma is said to be produced whenever the electron is liberated out in the form of ionized hydrogen. Okay, the second point is that artificial sun on natural earth. Recently, we are familiar one news that artificial superpower sun launched in the sky of China. So this is exactly the same thing. Okay, so how to create artificial sun on the earth? This is through plasma technology. And plasma, as we know, that at high temperature it happens. So how to confine it? So general materialistic substance, whatever materials we are familiar with, those materials cannot be utilized in order to confine the plasma. So what are the confinement techniques then? So this is your magnetic confinement, then again inertial confinement carried out at the cost of intense lasers, energetic particle beams. Then naturally confinement is also found, as in the case of astrophysical objects, including our sun, where gravitational confinement is operating. Okay, and in order for this confinement, one criteria is there. This criteria is called your Lawson criteria. According to this, the plasma density or concentration into confinement time, it should be a constant. And what is this constant? Constant value is varying from this. Okay, so this is your second per centimeter cube. So this condition has to be fulfilled. So as per that, if the density is high, accordingly that confinement time has to be accordingly modeled or according to go. Okay, otherwise it is not possible. So another important point, that artificial sun that is produced at the cost of your tokamak. So everybody knows what is tokamak. Tokamak is Russian word. Tokamak means your toroidal chamber and magnetic coil. Okay. So this is a device with the help of which artificial sun or star-like situations, environments can be produced even at the surface of the Earth. Okay. And this tokamak is one of the several types of magnetic confinement devices. Okay. And which is done with the help of various types of magnetic case confinements. Okay. Okay, fine. This is one picture taken out from this website. So this you can see your jet tokamak in UK and what is the size. You can see the dimension of this. Okay. Okay, fine. So this is one fusion occurring in the nature. Okay, our sun. So in case of our sun, we already know that this sun is again plasma fireball. Okay, so in this sun, how energy is generated? This is again through this your nuclear reaction, which is given in this form together with release of this much amount of energy. Okay, this much amount of energy. Okay, okay, fine. So this energy is produced with the help of only one hydrogen atom. Okay, and there are several. So how the total energy comes out, that is through this thermonuclear mechanism. Okay, fine. So this is ITER. ITER, everybody knows, International Thermonuclear Experimental Reactor, and it is going to be operated in this year, and this is $25 billion mega project, and that is going to give this much of megawatt of energy for this much of time. Okay, so this is we'll have to wait to get this, and our India is also a member of this huge international project. Okay, and now I told you in the very beginning that we work generally in this field, in this phase diagram. Phase is defined by your number density and temperature. And from this, your quantum plasma or your dwarf plasma that occurs in this region, that is your density is high and temperature is little bit low. So here in this region, okay. So in this region, this occurs. Okay. Okay. Okay, fine. So astrophysical realization of plasma, there are many, starting from your dust molecular clouds. Okay, and stars are formed in the dense sites of the interstellar space, which are known as dark molecular clouds, and the production structure formation takes place through the process of your gravitational instability, which is also known as Jeans instability, by which huge large clouds, global clouds, get fragmented into local cloudlets, and these local cloudlets further undergo gravitational collapsing, and due to gravitational contraction, what happens? The temperature rises, and to such a value that thermonuclear reaction starts, and as a result of which this core starts shining what we term as your gravitational star or stellar objects. Photostars after that stars. Okay, so in this case, hydrostatic equilibrium is defined only by your radiative force, and this is your inward gravitational force, and this is your gravitational force, and this is your radial force, that is at the cost of your contraction. And in the dust molecular cloud, as you know already, these are your dust grains composition, and these are your hydrogenic ions, and this is your electrons. And at the same time, the Jeans instability or the structure formation fundamental condition is that mass of the dust molecular cloud must be greater than the critical Jeans defined mass, and accordingly, your free falling time scale must be less than sound crossing time scale. If you analyze this thing, then we'll get this point, and this is well defined in several references, basic books. Okay. Okay, so now our question is, this is all about classical plasma. What about the quantum plasmas? So let us now introduce the fundamental differences between classical and quantum plasmas, and accordingly, already classical plasmas are well defined. Now quantum plasma, it is just antagonistic to this thing, this classical plasma. So this is just opposite. Behaviors are just opposite. What are oppositions? Oppositions are your low density here in the classical domain, here high density, then high temperature, yeah, low temperature, and at the same time, when to apply quantum mechanical formalism, this comes through this de Broglie's wave particle dualism. According to which we see, already we know from this equation that de Broglie wavelength is given by your Planck's constant divided by mv with usual notations. Now, already this order is well known. This order is everybody knows. In SI unit, 10 to the power minus 34. If the density is lowered to such a value that de Broglie wavelength becomes comparable to interparticle distance, in that condition, the classical formalism cannot be applied. Instead, we prefer to apply quantum mechanical formalism. And this is the just basic of quantum plasma scenarios. Okay. So accordingly, natural occurrence of various quantum plasmas, these are starting wide range. It has wide range existence. So electrons, gases, metals, then semiconductors, then metallic nanostructures, then interiors of compact astro objects, what I'm going to deal with. Then again, intense laser matter interactions. And this is one famous Hertzsprung-Russell phase diagram. So a phase is defined by your temperature and luminosity. So here it is the region where compact astrophysical objects are sitting. Okay, white dwarfs. So this is the region. Okay, I told you that your density should be comparatively high, but temperature should be low. So this is defined in this region, and this is, everybody knows, this is the main sequence. Okay, fine. So everybody knows the life cycle. So again, I repeat one information. The information is that the compact astrophysical objects, whether it is neutron star or white dwarf or even a black hole, these are the results of your instability in gaseous nebula. Or we can, at the same time, we can also say that these are the end results of your stars or supernovas, depending on the initial masses. So how? So if the initial mass is defined from your on the order of solar mass, in that case, the white dwarfs are formed, and these are again compact. Compactness is decided with the help of your material density. For example, in case of white dwarfs, on the order of your solar mass. Okay, so in that case, your density is about 10 to the power 12 SI unit. So for your white dwarf, so your density is 10 to the power your 12 SI units. That is your kg per meter cube. In case of your neutron stars, that is again further compact. And if the initial mass or the dying star has mass from in the range 1.5 to 5 solar mass, in that case, your material density, this is again 10 to the power now 17. And again, in the case of your black hole, the dying star has mass greater than 5 solar mass. Okay, 5 solar mass. And the density is accordingly is your very high. So high that gravity, nothing can come out of it. So this is your 10 to the power 30 SI units. Okay. So our aim is to discuss or to semi-analytically model your white dwarfs. So this is the reason of our exploration now. Okay. So plasma formalisms, and accordingly, plasma formalisms, as we know, there are various. So out of that, 4 are more important. So one is your single part orbit theory or single particle theory. It is done only in the case of very, very rarefied plasma. One is your electrodynamic, okay, and other is your magnetohydrodynamic, and finally one is your kinetic theory. So out of that, what we are going to apply? We are going to apply this theory, but modeled with quantum mechanical corrections. So quantum mechanically modified, this formalism is going to be applied. Okay. Okay. So fine. Another important, most important, unique. At that time, I mentioned that it is a unique property of ballistic dynamics. What is that dynamics? So whatsoever be your polarity, if we apply a potential in the plasma, what would happen? Opposite charges. The opposite charges are coming to screening it out. So this screening is called device screening. And because of that, the vacuum electric potential, which is called Coulombic potential, that is your unscreened potential, given by just 1 by R, which was 1 by R dependency, is modified in the form of your Debye-Hückel, in the form of Debye-Hückel formalism, and this is given by your this thing. Okay, so So we can show here directly. So, okay, fine. So this is the modification. Okay, so this is your device screened electrostatic potential. Okay, and this is your normally known Coulombic potential. And because of that, what happens? We can see there is a difference. So this difference, and this is caused only at the cost of your plasma effects. This difference, I think this is visible. Okay, so because of that, what happens? Your Coulombic potential is modified in the form of a screened potential, and at the same time, the exchange particles, which in case of electrostatic force field, it was well known as photon. These photons are behaving as if they have non-zero rest mass. So just one simple calculation will justify this. So what is the range? Range is your debye length. Debye length is the radius of this, or the radius of this shielding radius. Okay, and after just applying one uncertainty principle, what we can get, this range comes out to be of this form. Now, if the mediating particle or photon has rest mass equal to 0, if we substitute, then what happens? Your lambda d tends to infinity, which means that your debye screen potential goes to behaves as Coulombic potential. So under this condition, what we can say, in case of debye screen potential, the mediators are not massless against those found in the case of your Coulombic interactions. Okay, and because of that, many collective dynamics appear in the form of various wave excitation processes. And another important point is that on a global scale, plasma is known to be quasi-neutral, but on a local scale, just on the order of debye length, this is your non-neutral. Okay, and this is again fundamental concept. And this, because of this, we can say various wave excitation in the form of C. What are the waves? So wave excitation can be analyzed or can be understood with the help of the basic picture of a spring mass system by analogically this. Okay, so everybody knows that spring mass system that oscillates only because of the competition between inertia and elasticity. So inertia is provided by the ball and the elasticity by the spring. Analogously, in the case of plasma, depending on the number of constitutive species, there may be a number of collective wave excitations and oscillations. Okay, so this is again well known in the coordination space. This is executing in time frame just this type of wave. Okay, and in phase space, this is just like circle or ellipse. So it is ellipse. This is an ellipse. Okay, okay, and at the same time, let me understand another point that these acoustic waves, these are longitudinal waves, and accordingly, these propagate this way. So this is your just like a progressive wave, it is propagating. So in case of progressive wave, what is there? Phase velocity, your group velocity is not equal to 0, as a result of which it starts propagating. Okay. Then again, this is transverse wave. This is also excited in plasma, but not mechanically. This is at the cost of some other electromagnetic force agencies on being applied. Okay. Okay, fine. So our distinctive features, wave. So I told you that your oscillation becomes wave if the group velocity is not 0, or your wave becomes simply oscillation if group velocity is 0. That's all. In the earlier case, what we didn't have only omega t. In that case, it was just oscillation. And the same. There is no change of location. Okay, fine. Okay, fine. And already I have mentioned that this oscillation takes place only because of your competition between inertia and elasticity. Okay. Okay, and these are again basic points everybody knows. So presence of plasma species actually decides the total number of wave excitations possible in that plasma system. So accordingly, for normal two-component plasma, you can get electron acoustic wave, electron plasma oscillation, ion acoustic wave, and ion plasma oscillation. Okay, fine. So now in this quantum plasma system, what we consider that these are the originalities what we consider for the first time here in our model, that Bohm potential contribution, at the same time viscoelasticity. And viscoelasticity comes only because of your strong correlation, collective, cooperative correlation among the constitutive species, particularly heavier nucleus. Okay. So accordingly, our physical model we consider this way. So this starts from our work, that degenerate quantum plasma system, multifluidic model, and relativistically degenerate within inner core, and non-relativistically degenerate out in the electrons in the outer mantle, and your mixed action of your Coriolis force, then confinement pressure. This is also we are considering for the first time. I am discussing later. Then self-gravitational effect, viscoelasticity, and bomb potential together. And the situation is just modeled, keeping in mind in the core and mantle region of the spherically symmetric white dwarf. Okay, so this is the schematic picture, what we are considering. And our consideration is we will be considering only this region, this central region. Okay, so core and mantle. Okay, so as per this, so relativistic and non-relativistic electrons will be considered separately. Okay, then how to mathematically model. So first of all, what constituents we have? We have your electrons, light nuclei, and heavy nuclei. So for electrons, quantum mechanical treatment, quantum fluid. So accordingly, we have used your continuity equation in spherically symmetric geometry. That is, spherically symmetric geometry is considered only because of 2 points. Number one, it is simpler, by which three-dimensional problem r theta phi dependency disappear in the form of only radial dependency. And second point is that compact astrophysical objects are stable against radial perturbations. That's why we have considering only spherically symmetric system. And this equation is your continuity equation in spherical geometry. This is your momentum equation. And here the population density of electron, this is space-time, r and t, and this is your velocity of electrons. And here, this is your electrostatic potential. This is the pressure, total pressure on electron fluid. And this is the quantum mechanical effect on electronic dynamics, which is called bomb potential. Okay, and this is polytropic equation of state. And this is your polytropic constant. This is your polytropic exponent. And polytropic exponent models whether non-relativistic or relativistic dynamics. Okay, and night nuclear species are modeled accordingly, but here with quantum mechanical contributions completely detached, only classical fluid. Okay, so here you can see this is your isothermal pressure modulated by your confinement pressure as well. And this is your heavier nuclear fluid. And this is now modeled with the help of additionally viscoelastic effect. So this is called viscoelastic relaxation time. And we are considering one is your shear viscosity and bulk viscosity. Shear viscosity opposes your velocity or motion, and your bulk viscosity opposes radial expansion of the system. And these are all usual notations, completely usual. Okay, and after this, okay, these are our coupling equations. What are the coupling equations? So electron, then your light nuclei and heavy nuclei, these are coupled. These density fields produce your electrostatic potential distribution. Again, material fields. So electron is tiny, therefore their inertial contribution or gravitational contribution is totally ignored. So only contributing agencies or contributing factors are your light nucleus and heavy nucleus. So these density fields, material density fields, accordingly produce your gravitational potential distribution. And these are the standard astrophysical normalization schemes what we have been adopting. Okay, and these are all usual notations. Okay. So after this is again accordingly the same. So now we are interested in scale invariant treatment of the system. So that's why we are normalizing the system, making it thereby dimensionless or scale free. So accordingly, the normalized equations are accordingly given as this form. So these are various notations. So first one is your 12. This is your continuity equation. This is your momentum equation for electron dynamics. This is for your similarly the same equations for lighter nuclei, and accordingly we have the same for your heavier nuclei. And these are the corresponding electrogravitational Poisson's equations in respective normalized forms. Okay. So now already I told you that we are interested in radial perturbation, and because of the physical reasonings we have already justified. And accordingly, the perturbation, your radial wave perturbation analysis has been carried out in this direction. And these are the linearized equations, and these are to be put in the Fourier space or wave space defined by your omega k. Okay. And after that, these are again all the linearized equations. Okay. So after Fourier analysis and by applying the method of elimination simplification, we finally get the above system decoupled in the form of a degree 7 polynomial equations. So here the degree of the polynomial is 7. That is septic polynomial equations. Okay, and accordingly, it is very the mathematical construct looks very complicated. And since we are interested only in the nucleus acoustic wave, already we know that this is the heavy inertial species constituting the system. Therefore, we can apply one approximation, that low frequency approximation. So on that supposition, that complicated equation, the previous complicated equation now reduces to a very, very simple form. Yes, very, very simple form. Now, these are the various coefficients. Now, this equation has been just numerically analyzed to study the corresponding stability behaviors of the system. Okay, so these are the numerical results. Accordingly, so here, the ratio of your charge densities of the heavy to light nuclear species. Okay, so it has been varied, and accordingly in the relativistic, accordingly in the two regimes. One is your non-relativistic, and other one is your relativistic effects. Okay, so this is your non-relativistic electrons, and this is your ultra-relativistic electrons, and this is the couple dynamics together. What is happening? So we can see from here that this your kappa varies from this to this, and here you can see that as we go on increasing this mu value, mu is the density ratio, then what happens? It gets, the growth rate gets just decreasing. It has decreasing propensity in the low k regime, just less than k. Okay, and on the other hand, we are getting again similar behavior even in this section. So this is repeatedly showing that this parameter, that is the density ratio, charge density ratio, acts as a stabilizing agency for our compact astrophysical object under consideration. And this is only because of a new type of gravity electrostatic coupling inside that, and this which is revealed with the help of your Poisson equations already I have shown. That is closure of the system. Okay, and another important point we can find here, that again similar is the behavior, and here instead of your parameter of our variation is a nuclear charge to mass coupling parameter beta, and these are already defined. So accordingly, we find that in the k equal to this region there is no variation, but as you go in the high frequency domain, high k domain, then we can find that it is just your decreasing. Okay, so here from k it is increasing. Okay, and here it is from your different values, it is just we can say it is just increasing. So therefore the system gets destabilized in both your non-relativistic as well as in the ultra-relativistic regime of electronic dynamics. And this is again the coupled dynamics at the same time, so as to compare, get a common comparative footing of both the regimes under consideration, so as to consider in the electronic frame of reference as far as your this charge to mass ratio coupling parameter is concerned. So within that, we have inferred that this charge to mass coupling parameter behaves as a destabilizing parameter for the instability under consideration in your low k regime. Okay, fine. Then again, similar is the case. Here it is already I told you that what are the different parameters you consider. One of that was your Coriolis force. So because of this Coriolis force, what is happening? We are finding that as this parameter increasing, then what we are getting, it is just a growth rate is decreasing here. And here again, just as we go on doing the same operation, so here also we are getting this is the reverse thing. Okay, so here again it is increasing, here also it is just increasing from here. So accordingly, both the variations are plotted together. One is your in the non-relativistic electron dynamics, and other one is your ultra-relativistic electronic dynamics. So whatsoever we got here, that destabilizing behavior, again destabilizing behavior. So we are getting that this Coriolis force acts as a destabilizing agency to the white dwarf configuration under consideration. Okay, so this is again the complex gravity electrostatic coupling of your nuclear species with the quantum mechanical fluids of electrons. Okay, so another important point. So whatsoever we got up to this from figure 1, then again figure 2, then again figure 3. So these are further confirmed with the help of color spectral profiles. So we have defined color map, color space, and within that, again, what we find that here growth rate value, this is the value, red, that is low value. So low value is observed only in the gravitational domain. That is your K is very small, so as to make the wavelength is very large. Here again, same is the case. And these two panels, one is your upper panel and another is your lower panel. These are relating to your non-relativistic regime and ultra-relativistic regime of the electronic dynamics under consideration. Okay, so we can ensure, we are sure that the numerical analysis carried out so far are exactly correct. Okay, so what are the main conclusions we have derived? So conclusions are, first of all, a generalized hydrodynamic model has been developed, okay, for the first time to investigate the excitation and propagatory dynamics of nucleus acoustic waves in a gyrogravitating complex quantum plasma system resembling that inside the core of your white dwarfs. Then again, it concurrently considers the effects of Bohm potential, cell gravity, confinement pressure, Coriolis rotation, viscoelasticity in a spherically symmetric geometry without invoking any kind of quasi-classic approximation. So I would like to highlight here what is this quasi-classic approximation. So in the domains of astrophysics as well as fluid dynamics, we find many non-planar problems are worked out with the help of planar approximations. That is, the geometry is considered is spherical, whereas the stability, linear stability, is considered at the cost of your plane wave analysis. So geometry is spherical, that is your non-planar, whereas the wave consideration is planar, so that seems to be inconsistent as well as improper. So what we have considered? We have considered a spherical geometry, but the perturbation is also spherical. So this quasi-classic approximation is your K star, this is your wave number, and this is our position, xi, which is much greater than 1. This is called the quasi-classic approximation, and application of which in the WKP approximation reduces the perturbations to behave as your plane wave. It is given in most of the astrophysical books, including that by Subramaniam Chandrasekhar also it is available. Okay, fine. Then at the same time, so our conclusion is calculation is more generalized because it relaxed. This quasi-classic approximation is relaxed in our analysis. Another important point is that a restricted spherical wave analysis yields a generalized dispersion relation. So see, our equation is septic in nature, and without applying any kind of or invoking any kind of approximation or homogenization approximation or principle. Okay, so that is exact calculation analytically obtained the dispersion relation. Okay, fine. Then we further found by this semi-analytic analysis that the ratio of heavy to light nuclear charge densities, that is mu, acts as a stabilizing agency as ensured by reflected in figure number 1. At the same time, relative nuclear charge to mass coupling parameter, that is beta, acts as a destabilizing parameter. That is also ensured in figure 2. So we can further go in figure 2 again. So this is figure 2. So here also we find that destabilizing agency. Then at the same time, here again, we further find that the rotational force acts as a destabilizing source. Again, further go to figure 3. Yes, the rotational force acts as a destabilizing agency here. Okay. Then at the same time, what we can further see that the results whatsoever discussed above, whatsoever explored above, are exactly corroborate with that found in your color spectral profiles given by figure 4. Okay, so here again we find again the same case, same thing, that at what region the growth is your minimum. Okay, so fine. So we are getting in full agreement, fair agreement with your earlier analysis in both the sections. Okay. Okay, and for example, from the implication and application point of view, already I have mentioned that this situation, this model was done keeping your white dwarf interior in mind, and accordingly, this theoretical formalism can be well utilized to study various stability problems of compact astrophysical objects, including your white dwarfs. So whenever there are multi-nuclear species and quantum mechanical fluid of electrons are there. So it can applicable not only to your white dwarfs, but also your J planets, that is your Jovian planets, where different species are there just behaving like your nucleus, or nuclei can be exactly replaced with the help of corresponding other molecules at the same time. Then again, neutron stars as well, this formalism. Okay, so this is one semi-analytic explorative study. Okay, and application that what parameter plays in what role in the case of your even neutron star glitches. That is also we have not discussed here, but that is another application or extension maybe from this problem. Okay, fine. So these are various references out of this. So this nucleus acoustic wave we have also tried a few years back also. It has been going on. So there are various references, and these are very interesting problems, interesting papers also here. So these are dealt in. This review articles also very good about these compact astrophysical objects and quantum plasmas. Okay, so there exists a very good quotation by Sir Albert Einstein. So once we accept our limits, we go beyond them. So I tried whether this is applicable even for me. So I told you that although the work is published in Nature group of journals, but that paper has many shortcomings, several shortcomings, because these were the first initiative from us from the theoretical perspective, with semi-analytic formalism. Okay, so we tried to make it, and we know that there are different dwarfs. Okay, for example, we have dwarfs that is called brown dwarf, which has mass between 0.01 up to 0.08, and composition is your electron and your hydrogen nuclei. Okay, so for that, at the same time, we model the relativity effects only through your equation of state. So we have just corrected it. Then again, at the same time, you have again helium dwarf, which has mass on the solar mass scale 0.08 to 0.25. Okay, so that is again explosion type is planetary nebula. Okay, then again we have again carbon oxygen white dwarf, where the mass of the dying star is on the solar scale 0.25 up to 8 solar mass. Then again another, we have multifluidic system, that is your oxygen, neon, magnesium white dwarf. It has mass on the order of your 8 to 12 on the solar mass scale. Okay, so here, so this modeling, this magnesium white dwarf model, that is oxygen, neon, magnesium white dwarf model, these are again not done. Then again at the same time you have neutron star supernova as well. So mass already I have mentioned. Okay, so there are various situations where this model needs to be improved. This model needs to be refined. Only then this can be utilized. Okay, and at the same time we are considering only one mode, nucleus acoustic mode, whereas in the case of your neutron star there are fundamental, which is called F mode, then again pressure P mode, then again gravity G modes, then again rotation Coriolis mode, that is your R modes. And another most important point, which is a relevant topic of this discussion, but I have not included, that is your modes coming out because of space-time fluctuations or space-time instability, which is called W modes. So these modes are again future perspectives, future problems, if possible we'll try. Okay, so based on this, what I mean to conclude is that the one limitation has been solved, and that limitation of our previous work results in this accepted paper, and this paper again by the same authors, Shayanti Dasgupta and myself, Pralay Kumar Karmakar, and this paper is appearing in the next week. Okay, just one extension, continued study of the previous work. Okay, so thank you very much for your kind attention. So thank you, and I'll be happy to answer if there is any query. So thank you so much.
Thank you, Dr. Kormakar, for your nice presentation. And in this platform we are meeting again because initially we thought that we will meet in offline mode, but because of this corona we cannot meet. But anyway, I can see many of our colleagues are joining in this platform. So this is the last session and the last speaker. And now I request participants if they have any questions or not.
Excuse me, I'm Indu. I have few queries to ask. Can I go?
Yeah, please.
So it was a nice presentation. I understood a lot. So from the very basic level, but I probably missed a few things because as the white dwarfs are generally, they have magnetic field of the order 10 to the power 6 to 10 to the power 9 Gauss, right?
Right.
But here probably you did not consider the effect of magnetic field. Maybe
Yeah.
since these are instabilities, in local level, probably magnetic instabilities which also contribute, and probably this instability may also like make it more unstable, or maybe growth rate will maybe increase or decrease. Can you like comment something, or how the
Right.
how the magnetic field
So that was also mentioned in my schematic diagram as well, that magnetic field, all the relevant properties, these are also there. But this is one idealized model. We just wanted to have in the very your low frequency domain. So you see, so dispersion relation degree was 7. Out of that, we have simplified it and we have just studied only this. So there are many more things yet to be studied. So magnetic contributions have been totally ignored, I admit it. So these are left for future refinements. Yes.
Can I ask one or two? Like, but how you decide that you are in relativistic or ultra relativistic or non-relativistic limit? You are means around the black hole, or means around the core of the white dwarf, right? And what do you mean?
Core, and at the same time, just let me. Okay, so core and just after that core. Okay, so your mental is also there. So, okay, so there you can see already schematic diagram. It has been given that it is already given in the literature that in the core that is your ultra relativistic, but just above that it is your non-relativistic. Okay.
What is deciding that electrons are relativistic or non-ultra-relativistic?
Oh yeah. In our equation, polytropic equation of state, there is one polytropic exponent. So exponent value, as was done even by Chandrasekhar in white dwarf theory.
Polytropic index you are talking
about.
Right.
Yeah.
And what can be the observational implication of these acoustic waves if we want to observe, like white dwarf, we want to observe, or what kind of observation implication it may have?
Oh, observations, just like your heliosismology. So here also astroseismic devices are there. So for example, your interferometric, then again power spectrum analysis. Okay, so I can just admit that this is a theoretical work we have just done, and this is explorative. So just comparison, for the sake of comparison, we have not done rigorously anything. Okay. And it is quite similar, just like what I told you, that your P mode, that is pressure mode, which is acoustic mode, or G mode, that is your gravity mode, and again, buoyancy driven mode, F mode, just in the case of your heliosismology. So that is similar. So how these helioseismic modes are detected, various devices are there, both ground-based as well as multi-satellite techniques. So by that, we can have different power spectrum. By that, we can analyze just by comparison. See, any stars, for example, sun, which is inaccessible to any kind of probe or device. So these are just in situ measurements from distance, okay, by distant analysis of your power spectrum. So by that, it can be done. So this is also left for, we have some limitations. Within that, we have just given one semi-analytic formalism. Yes, these are the things yet to be improved in the future, yet to be refined in the future. Okay.
Thanks a lot for your...
Okay, thanks a lot for your suggestions. So these are points as per our quotation by our Einstein. In the future works, these are going to be addressed. Thanks a lot.
Yeah, so thank you very much for this nice discussion. So is there any announcement there from the organizing committee? Any announcement?
Yes. Okay. Thank you all for your patience and attention throughout the afternoon session and for all the questions and answers. So I would like to thank Professor Himadi Das for coordinating the afternoon sessions smoothly and nicely, and all the others today's speaker so for presenting their current works. So I think with no other speakers left for today, I think I would like to bye-bye for today here. And we'll meet again by 9:50 tomorrow morning. And all are requested to make the NEMA-VII edition most convenient by joining the program timely tomorrow. I think till then, thank you all once again, and goodbye to all, sir.